Hello, everybody. Welcome to your next lecture in oceanography. We're going to be talking about all those lovely waves that you know and love from the beach. We're going to talk about all the juicy scientific details about how they form. So brace yourself as we go on through this lecture on waves today. So, waves, of course, you're familiar with waves at the beach. They do not consist actually of traveling water. So what do I mean by that? I mean, it's not that the water is kind of moving from one place on the left side of your screen and moving to the right place. So the right side, right? So the water itself isn't actually carrying and moving along. Otherwise, if it was moving along, you could just sit on the surface and be carried along by the waves, and that doesn't really happen. So what actually is happening is that waves are moving in a orbital pattern. So you could see on the screen here how you have these kind of node points that are just being moved, not from left to right across the screen, but they're moving in circular motion. So every single one is moving in a circular motion. I want you to notice that as you go a little bit deeper, right, you see this as you go a little bit deeper, the orbital motion becomes smaller and smaller and smaller. The radius of the orbital motion becomes smaller and smaller and smaller. So how does water move in the ocean? As an ocean wave passes through, it moves in an orbital manner, moves in a circle, basically. Okay, so that's the answer to number one. So just a little bit of anatomy of a wave, so you know what all these different words mean. So this is important to pay attention to. You have to label this on your diagram. So the top of the wave right here is called the crest, right? The bottom of the wave here is called the trough. Okay, so we have the trough and the crest. It's the high point and the low point of the wave. Now the length from crest to crest, or trough to trough, is called the wavelength. Wavelength, you'll see, is extremely important as we go through this lecture. So make sure that you understand what that means. So wavelength, very, very important. The amplitude of the wave is kind of the distance from the sea level, the normal sea level, to the crest, and that would be the same as you could also measure it from like the normal sea level to the trough as well. That would both be the amplitude. The wave height is 2 times the amplitude. So 2 times amplitude is equal to the wave height. Okay, so that's the height from the trough to the crest. Okay, so that's all you need to know about kind of the anatomy of it. Now, wave frequency and period is also important. So the wave frequency is the number of waves passing a certain point per second. The period is how long it takes a wave from crest to pass by a certain point. Okay, now the frequency is actually equal to 1 over the period. Okay, and vice versa, the period is equal to 1 over the frequency. Okay, so we can actually measure, just looking at this GIF little movie file, you can actually measure, well, the timer already went, I can restart it, but you can actually measure the frequency and the period here. So I'll restart, let me restart this, so I'm trying to restart it. Okay, so we'll be careful more next time, but let me try to restart that timer, and we'll actually measure the number of waves that pass by, let's say, the edge of the screen in 10 seconds. Okay, so 1, 2, 3, I'm counting over here, 4, 5. Okay, and so there were 5, you saw that there were 5 per 10 seconds, right? So there are 5 waves per 10 seconds. So what is that frequency? That is equal to 1 over 2, 1/2 per second, okay? Per second. And by the way, a per second, we actually have a unit that means per second, and that's called a hertz, right? So it'd be 1/2 hertz. Okay, so the frequency of this wave that you're looking at right now is 0.5 hertz, right? 0.5 hertz, or 1/2, 1 over 2 hertz. Now, of course, the period, how do you calculate the period? So the period would be 1 over the frequency, which would be 0.5. So that would be equal to, per second, so that would be equal to 2 seconds. okay, right? So 1 divided by 0.5 is 2, and so you end up with 2 seconds, okay? So the period of this wave is 2 seconds. So that's how long it takes to go from crest to crest. So anyway, let's go on to the next one here. Now, ideally, waves move kind of like an ideal wave just moves in kind of an orbital fashion, but realistically, in the real world, waves do kind of carry objects along on the surface a little bit, and that's known as Stokes drift. So you'll see, actually, if you take a look at this wave versus this wave, do you notice how this one actually looks a little bit more like a real ocean wave? And the reason is because the water at the top is doing larger orbits than the water at the bottom. You see that? And so things actually get carried along because they're moving a little bit faster on the top than they are at the bottom at the trough. So when they're moving at the crest, they're moving a little bit faster than they are in the trough when they're receding in the trough. Okay, so things get carried along by waves in that way. Okay, so anyway, so we're down to number 5 right now. We talked about wave frequency, talked about wave periods. Number 5 says, how do circular orbits of water motion change as you go deeper into the column of the water? So you might have seen in these diagrams, things like this, the water is moving in larger orbits near the surface, near the crest, than it is in the troughs. Okay, so as you go deeper, that orbit becomes smaller and smaller and smaller. Okay, so let's talk a little bit more generally just about waves in general. So what I mean is not just ocean waves, but any kind of wave, because there's lots of different kinds of waves. There are ocean waves, there are seismic waves, there are sound waves, there are light waves, electromagnetic waves, all sorts of waves. And all these things have something in common, in which there's always this kind of this rotary, reciprocal, repeating motion, right? Rotational motion that's going on. Now, waves in general always have a disturbing force. So in the ocean, there's a disturbing force that causes mechanical energy from the disturbance to propagate, and it propagates through the ocean surface water. And in the ocean, the disturbing force is usually wind, but not always. There are some things that can disturb the ocean surface besides wind, and we'll talk about those different things in a bit. So what happens, you can also have storms, you can also have earthquakes, landslides, and of course tides are another huge kind of wave. Actually, we'll find out later, tides are actually kinds of waves. But tides are also a disturbing force. It's a gravitational, I guess the disturbing force is a gravitation, of course, from the moon or from the sun or what have you, right? So there are different disturbing forces. Usually it's wind, but not always, okay? So now with waves just in general, just generally speaking of all waves, you have a disturbing force, and what happens is you have an overcompensating restoring force. So, if you consider this weight on a spring, the weight gets disturbed, the spring tries to pull it back, but it overcompensates, right? It overcompensates. It's too strong. And so the disturbance just keeps propagating and propagating, going on and on and on, okay? So in most cases, gravity is the restoring force for ocean waves. So if the surface of the water gets bumped up or down, gravity is trying to restore it back, but it overcompensates, and that's what creates this propagating wave. So one exception to gravitational restoring force is what are called capillary waves. These are very, very small waves. I don't talk about capillary waves very much just because they're not really very important for us in oceanography. They do exist. But capillary waves are these very, very small little, maybe you might call ripples on the surface. I'm sure you've seen these before looking at ocean water or whatever body of water. They're little ripples on the surface of the water that are usually caused by a light wind, and the restoring force is actually not gravity, but the surface tension of the water. So surface tension can be a restoring force, but usually gravity is the restoring force for ocean waves. Okay. Now, like I said before, tides are actually just enormous waves. They're just huge waves, and the wavelength of the tide is equal to half of the Earth's circumference, right? Because remember, we learned from tides that you have a high tide on either side of the Earth, right? And so the wavelength from crest to crest, right, it's half the Earth, right? Or in the case where you have, neap tides, it could be 1/4 of the Earth. It depends how many tidal bulges that you're going to have on that particular day. So it could be 1/4 the circumference of the Earth. But anyway, the main point is tides, they're just big waves. That's all they are, huge waves with huge wavelengths. Okay. So maybe this little time-lapse video might help you kind of imagine the tide as a wave. So we're going to look at the tides at the Bay of Fundy, which we talked a lot about, but it's maybe going to help you kind of visualize things as tides as a wave. So if you look at the time lapse, the 45-foot tides from the Bay of Fundy coming in and going out, you'll maybe kind of see what I mean here. Right, so here comes tide, outgoing tide, right? And then you see the incoming tide. And of course, it's not breaking like a wave usually does, but gosh, when you speed it up, it's really acting a lot like a normal ocean wave, right? Doesn't it kind of just look like a normal ocean wave when you speed it up like this? So if we just repeated this video over and over, it would just kind of look, and if we had to speed it up even a little bit more, you would just kind of look like a normal wave. The water comes in, the water goes out, the water comes in, water goes out, right? So tides are waves, right? Another really kind of important wave we talked a little bit about in the tides lecture are what are called Seiche waves, or I should say what we will talk about in the tides lecture are Seiche waves. So Seiche waves are large waves that result from strong sustained winds or atmospheric pressure differences. So what happens is this. Let's say that you have a really strong wind and you have a body of water and it blows very strongly, and it'll actually build up the water on the leeward side of the or the windward side, I mean, of that body of water. So there's the blowing sustained winds build that up that way. Okay, so what happens is after the winds die off, what's going to happen? The water is going to return and refill that missing void right there. Does that make sense? Do you see that? So the wind blows the water. It kind of makes a high setup of the water over here on the windward side of the lake or body of water. And then when wind dies down, it's going to return. And what you end up is actually kind of a sloshing motion. So the wind blows, it sets it up that way, and then it sloshes back and forth. So just imagine kind of a sloshing back and forth in that body water. So that's going to become very important when we talk more about tides later. So Seiche waves. Let's talk about all the different kinds of waves. This is a pretty good diagram that sort of breaks everything down in terms of waves according to their periods. What do I mean by periods? Periods, again, is the time from going from crest to crest. So if you have a short period, it's a rather small wave. If you have a long period, it's a longer wave, right? So tides have the longest periods, and actually this is kind of set up in a kind of an annoying way because the short periods are to the right and the long periods are to the left, which is reversed than what we're normally used to. I don't know exactly why they set it up that way, but oh wait, I think I see why they did that, because they're really ordering this in terms of frequency, not periods. So anyway, we have tides on this side. They have the longest periods, right? Because that tide takes anywhere from a day, to half a day or whatever, 6 hours. Depends what kind of tide it is. We'll learn more about that later. But it could be anywhere from 24 to 12 hours, 6 hours even, depending on what kind of tide it is, to go from crest to crest, right? Now tsunamis. These are big waves that are caused by seismic disturbances like earthquakes or landslides. They have they have also large wavelengths as well, large periods, I should say, as well. Seiche waves have slightly smaller periods, right? Then we have the normal wind waves. Wind waves are what we are used to. The everyday waves that we encounter at the beach are mostly wind waves. Okay, they're just the waves that are created by the wind. And then we have capillary waves, which are like the ripples on the surface that are very, very short periods indeed. Okay, so the storing force for all these is gravity, but except for capillary waves, which is surface tension. Okay, the disturbing force for all of these things is gravity for tides, seismic disruptions for tsunami waves, and wind for the rest of these. Okay, that's usually the disturbing force. Okay. All right, so going on, we talked about characteristics of waves, and a lot of these things, a lot of what we're going to see, the properties of a specific wave are determined by its wavelength. So that's why wavelength is so important. I talk a lot about wavelength. Remember, that's just the length from going from crest to crest, okay? So let's talk a little bit about wavelength. There's a relationship between wavelength and water depth, okay? So let's talk a little bit about this. We actually classify waves as deep water waves, transitional waves, and shallow waves based on the relationship between wavelength and the water depth. Okay, so let me say that one more time so you catch it. We classify different kinds of waves based on the relationship between the wavelength of the wave and the depth. We have deep water waves, transitional waves, shallow waves. Okay. So in deep water waves, you'll notice that the wavelength, of course, you know that the orbital motion decreases with depth, right? You already know that. So once you get to half of the wavelength, okay, length L, the wavelength, divided by 2. Once you get down to half the wavelength, there's really very little disturbance in the water column. So if you're down here, let's say you're diving, you're a scuba diver, and you're down here. You're below half the wavelength in depth in the water column. What you're going to find is that you feel nothing of the wave above you. Okay, now, and the wave itself does not feel the bottom. Okay, now once you get to this area, okay, you'll notice that now the wave has become shallow enough that the wavelength is actually greater than, or I should say, maybe the depth is what would be? It would be less than half the wavelength. So at this point, the wave starts to feel the bottom. Okay. Now, when you get to and even a more extreme case where like the depth is equal to the wavelength divided by 20 or something like that, then you are really getting highly influenced. The shape of the wave is highly influenced by the sea floor, and you get shallow water waves. Okay, so there's deep water waves, transitional waves, shallow water waves. So waves normally create disturbances down to half their wavelength in depth. Thus, the deep water waves do not feel the bottom because they're in water that is greater than half their wavelength. Okay, so you're going to see that, for wind waves, usually wind waves, they have wavelengths that are maybe like, 20, 30, 40, 50, 60, maybe 100 meters. But they're moving in water that is in the deep ocean, right? The deep ocean is 4 kilometers deep. So they're definitely not going to feel the bottom. They're going to be waves in the open ocean are mostly going to be deep water waves, okay? So shallow water waves, once those waves reach the coastline, though, then they start to transition into shallow water waves, and we're going to see that things are going to change, okay? So the reason that this is important is because the speed of an ocean wave is actually determined by whether it's a shallow water wave or if it is a deep water wave. All right, so for a deep water wave, what is the velocity of the wave? The velocity of the wave, how fast the wave moves, is given by the square root, so it's velocity right there, v. It's given by the square root of g, which is the acceleration due to gravity. It's 9.8 meters per second squared, times the wavelength. Here instead of L, sometimes I use L for wavelength. Sometimes I use this, which is lambda, which is the Greek letter for L. Lambda divided by 2 divided by pi. Okay, that will give you the velocity in meters per second of your deep water wave. Now I want you to notice something. This is the velocity for a shallow water wave. It is equal to the square root of g, which is 9.8 meters per second squared. It's always the same. It's the acceleration due to gravity. Because remember, the restoring force of this is gravity. So that's why gravity comes into play here. 9.8 meters per second squared times the depth. Okay, so it's the square root of the gravity acceleration times the depth. Okay, gravity acceleration is always the same. It never changes. It's a constant. It's about 10 meters per second squared. For the purposes of this class, it's okay to just round it off to 10, because just to make the calculation easy. 10 meters per second squared. The d is the depth. So notice something very important here. When you're talking about a deep water wave, let me erase the ink on this. Okay, when you're talking about a deep water wave, the wavelength depends on what? Do I ask about this? And I think I do. Yeah. What determines whether a wave is a shallow wave? Okay, what is the speed? All right, so a deep water wave, what does it depend on? It depends on the wavelength. Okay, all the rest of those things are constants. Okay, g is a constant. 2 is obviously just a number, and pi is a constant. The value of pi never changes. The value of g never changes. The 2 is 2. Okay, what does the velocity depend on for a deep water wave? Depends on lambda. Depends on the wavelength. Okay, that's it. For a shallow water wave, notice that lambda wavelength does not matter. Does not matter. Doesn't even come into the formula. All that matters is the depth. Okay. So when you're talking about a certain depth of water, like near the coast, near the beach, nothing matters except for the depth. So all the waves, once they approach the beach, they approach the shore. All those waves are just going to be moving at the same speed. Why? Because their speed is totally determined by the shallowness or the depth of the water. Okay. All right, for shallow waves. Whoops, that's supposed to be waves, not waver. What is the velocity of a wave moving through 2 meters of water? Okay, that is equal to the velocity equals the square root of g times 2 meters. Okay, that's equal to the square root of, I'm just going to round it off to 10. It's 9.8 meters per second. I'll round it off to 10. 10 meters per second squared times 2 meters, which is going to be equal to square root of 20 meters squared over seconds squared, which means, what's the square root of 20? Well, it's going to be somewhere between 4 and 5, right? Let's see what it is. Get our calculator out, and we'll put square root. Hello, square root, where are you? I don't see it. Do you see it? Is this it? Oh yeah, this one, square root of 20. So it's 4.47, like I said, between 4 and 5. So it's 4.47 meters per second. Okay, that's the answer. For a deep water wave, let me erase the ink on this slide. For a deep water wave, what's the velocity of a wave with a wavelength of 20 meters? Okay, here we're going to go square root velocity, and we're going to use a deep water wave. Okay, deep water wave formula. So v equals the square root of, I'm going to round it off to 10 meters per second squared, times 20, right? That's the wavelength, divided by 2, divided by pi, and I'm just gonna pretend that pi is right 3.14. Okay. What does that equal to? So that's going to be equal to the square root of 100 meters squared over 3.14 seconds squared. Okay, and what is that? It's going to be something like 30, square root of 30. So we'll see what that is. I got to get my calculator out again. So 100 divided by 3.14, whoops, 14, gosh, making mistakes, equals 31, right? 31.8, and we're just going to take the square root of that, and we get 5.6, okay? Whoops. And we get 5.6 meters per second. So there you are. That's how you do those calculations. You're not going to have this on the test in a really hard way. I might have you do like a shallow water one. I don't think I would have you do a deep water one. But definitely like a shallow water one. You might be on the test, okay? And it would probably be done in a way that's simple enough to do kind of in your head. All right, so tsunamis can have very long wavelengths, up to 200 kilometers or less, sometimes more or less. It could be up to 200 kilometers. So this creates a very fast-moving wave, right? If the wavelength is that big, it's going to move very fast. However, if you think about this, it really kind of depends on a lot of things, right? If you have a wavelength of 100 kilometers, the oceans are not 100 kilometers deep, right? They're not 50 kilometers deep. They're like 4 kilometers deep. So they're going to act like shallow water waves. But still, in the deep ocean, where you have a great depth, those waves are going to be able to move very fast. However, as they approach the coast, they're going to slow down a lot. So what you're going to see is that in the deep ocean, right, where you have depths that are 7,000 meters or 4,000 meters or whatever, you have wavelengths that are maybe 200 kilometers, right? And they're going to be moving really fast. Look at this, 400, 500 miles per hour. So the waves in the ocean are actually going to be moving like at the speed of like, a jet airplane, right? But you'll notice that as it approaches the coast, right, as you get into shallower water, the speed it's going to shorten up a lot. Now, I want you to notice something kind of interesting. Out here, the wavelength of the tsunami wave is very large, right? But as it approaches the coast, notice that it gets shorter and shorter and shorter. The wavelength is dissipating and shortening because it's slowing down. And so it's like the wave in front of the preceding one has slowed down. I think a really good way of imagining this is it's kind of like, like cars driving along on the freeway, and then they start to hit some traffic, or maybe more, they start to slow down. You know that when the cars start to slow down, what happens? When you're driving really fast, you're spaced far apart. Well, hopefully, ideally, you're spaced far apart. But then once you all start to slow down, you guys get closer and closer and closer and squeeze in together. Waves do the same thing. Ocean waves do the same thing. As the waves slow down, as they approach the coast, because they become shallow water waves, then they're going to get closer and closer together, and the wavelength is going to decrease, which in turn decreases the speed. Okay, so wind is the most. Now, tsunamis are kind of unusual, right? Wind is by far the most common disturbing force. So most of the waves that we see in the ocean are wind waves. Okay, they're waves that are sustained and disturbed by the force of the wind. So waves begin as capillary waves, and they progressively grow larger and larger, and they become, as long as they become deep water waves. So as long as you're a deep water wave, you can get bigger and bigger and bigger. How big can a wave get? A wave is only stable in water. A wave is only stable up to 1/7 of its wavelength. So if you want to know how big can a wave get, it can only get to 1/7 of its wavelength. So if you have a wavelength that gets up to 70 meters, you can only have a 10-meter high wave, which is a really big wave, right? That would be 10-meter wave would be a 30-something foot wave. Okay, that's very big. Now, once the wave gets so big that it exceeds 1/7, that 1/7 ratio, it's going to start to collapse. It's going to start to spill over the edge of itself, and it's going to create that white cap phenomenon. So maybe you've seen on really windy days, I know, like I see this sometimes. I'm driving over the bridge, and I'm looking down on the bay. It is a really windy day, and you're hoping you don't get blown off the bridge. and you're looking out and you'll see that there's all these white caps. They're called white caps. It's the frothy white foam that's forming on the crest of the waves out in the ocean, in the bay. Okay, what are those? It's the wave spilling over onto itself. And what that means is that when you start to see white caps, what it means is that those waves have gotten as big as they can possibly get in that sea, right? Because once they start to white cap, it means that they have exceeded the 1-to-7 ratio, the 1/7 ratio, and that's as big as they can get. They can't get any bigger. Okay, so we call that, by the way, we call that when they start to get to white cap, we call that a disturbed sea. A disturbed sea. Okay, so the regular smooth undulation of the ocean surface that sometimes you see, especially if you go out to the island and you look out, over the Gulf of Mexico waters, you'll see this regular dispersion of waves. And that's called a swell. Maybe you've heard that term before, especially if you're into surfing or you know anyone who's into surfing. They definitely talk a lot about the swell. Okay, the swell, that regular, smooth, undulating ocean surface where you get regular waves coming in one after the other, arises from a process called dispersion. Okay, it arises from a process called dispersion. So this is a regular separating out of different waves according to wavelengths. Dispersion is a regular sorting out of waves according to their wavelength. And it occurs because waves with a greater wavelength have a greater speed than those with a smaller one. So I'll give you a little video that kind of explains this. So let's say that you have the fetch is the area over which the wind is blowing, where waves can develop. So the fetch, the wind is blowing in the fetch. It creates a confused or disturbed sea. You get white caps, and it creates all sorts of different waves with different wavelengths. What happens is that as those waves propagate away from the fetch, they move away from the fetch, the bigger wavelengths are going to move out front, and the smaller wavelengths are going to lag behind, and everything's going to get sorted out into from confusion to like a very regular dispersal of waves according to their wavelengths. And that's because they get sorted out because the higher wavelengths have a higher speed than the lower wavelength waves. Okay, so that's called a swell. Swells developed from a confused sea. A confused sea is when you have a storm, you have a wind, it's blowing in the fetch, it creates waves of all sorts of different kinds of wavelengths, and then they get sorted out as they propagate away from the fetch. Okay, so when you see this regular movement, you see the swell, and you get this regular sorting out of waves in different wavelengths according to their wavelengths. We call that also a wave train. A wave train. So the last video wasn't actually exactly accurate showing how wave trains move. There's a really interesting picture just looking out, into the little bit of elevation. You can see the swell coming in, right? So you see this very regular pattern of different waves. So, actually, the way that waves propagate through the ocean is that a single individual wave is really only alive for a short period. And what happens is that waves constantly die and then new waves form. So every time a wave hits its crest, half of its energy goes to creating a new wave. And as it moves along, it dissipates by half, by half, by half, by half, till it dies out. So if you were to think of just this single wave right here, so we're just going to call this wave number 5 right here, and we're going to keep track of that wave. As it propagates, it gets smaller and smaller because it's going to just be giving its energy to the wave in front of it. Okay, it just transfers half of its energy to the wave in front of it. So wave trains, individual waves are actually moving twice as fast as the wave train because half of the energy is going to creating that new wave. Okay, so individual waves move faster than the wave train itself. Okay, so the swell, the actual wave train, the swell, is going to be moving only and propagating only half the speed of the individual waves. Okay, a fully developed sea refers to a sea with the maximum wave height for a given wind strength, fetch, and wind direction. Okay, so the fetch is the area over which the wind is blowing. Okay, the larger the fetch, the larger the waves you can get. Wind duration is how long the wind's blowing for. Wind strength is just the velocity of the wind. Okay, so once you get white caps, you have a fully developed sea because the waves have gotten as big as they can possibly get. Okay, for wind duration, to get a fully developed sea, you need often at 3 days of sustained wind. You can't have more than 3 days because after 3 days it just doesn't do anything. There's the conditions on Earth are such that you never get more development after 3 days. So 3 days is the maximum. Okay. Now take a look. These are actually a world satellite map of wave heights in the open ocean. In the open ocean. I'm going to talk about waves near the coast later. We're talking about the open ocean. So where on Earth do we get the largest waves? You'll notice that where we live in the Gulf of Mexico, we get tiny waves. You might have noticed that. We get really small waves here, actually. So here we are. We have very small waves. I grew up in California over here, and we get larger waves there in California. But you can see it's not terribly larger. Places like Hawaii get a lot bigger waves, right? So surfers always like to go to Hawaii because you get very, very large waves in Hawaii. Okay, why is that? Because Hawaii has much deeper water surrounding it than it doesn't have a continental shelf. It's an island out there by itself. But you'll notice that the largest open ocean waves are here in the Southern Ocean. Okay, and the reason for that is because now we learned before about the westerlies, right? Well, now the westerlies in the southern hemisphere are blowing like this, right? They're blowing from the west, and there's no continent to disturb them, right? So they're blowing without any disruption around and around and around and around the Earth. And that means it has an infinite fetch. You see what I mean? It can just blow uninterrupted around and around and around the Earth, and that creates an infinite fetch. And so that creates the largest waves in the open ocean. Wave heights that are 8 meters are not uncommon. 8 meters, right? 24-foot waves. So here are some videos of sailors in the Southern Ocean. And it's very daunting if you're on a sailboat trying to go across the Southern Ocean.
I don't think there's anything that we've seen so far that's going to compare to what we're about to encounter.
It's the unknown for the people that have never been down there. They've only got what they've read or heard about the Southern Ocean to go by.
I've never been in the Southern Ocean. I've never seen waves like I think we're going to see. Basically they're going to be like cliffs.
If it's a classic Southern Ocean, and it's shaping up to be. Already we're delaying the start for 2 days because we have one of the biggest weather systems coming through that we've had come through the South Pacific in the last 30 years.
This is what the Volvo Ocean Race is about. It's about leg 5.
Snow, icebergs, lots of wind. I guess you don't really know what's going to hit you.
The last time anyone sailed this leg, the boat that really tried to take it safe and slow down first was the only boat to sort of finish the leg unscathed, and I think 2 boats were dismasted.
There's no room for error when you're down south.
So anyway, I think you get the idea, right? These are really, really intense seas. The largest wave ever encountered on planet Earth was in the Southern Ocean by the U.S. Navy tanker, the USS Ramapo. Encountered it was in the midst of 67 mile per hour winds in the Southern Ocean, and the height was estimated at 34 meters. 34 meters, remember there's 3.28 feet per meter. So that gives you about 100 feet, right? So about a 100-foot wave, right? 34 times 3.28 is 111 feet, right? Or 112 feet. So tremendous waves. Oh, it was written right there. I didn't even see it. Okay, so I want to talk a little bit now about interference among waves. So it's often the case that multiple wave trains are interfering with each other and kind of overlapping with each other because they're different fetches in different parts of the ocean. They create swells, and the swells kind of collide. Okay, so you get interference between the different waves. All right, so interference among waves, and it doesn't matter if it's a sound wave or a light wave, creates a lot of really interesting phenomenon. So when two wave sets are in phase, that means that they are kind of overlapping each other perfectly with their crests. See how here the crests are in phase with each other and the troughs are in phase. Okay, you see that? What happens is they actually build each other up, and so that's called constructive interference. They actually construct something larger. They construct a larger wave. So you can see that these two waves can add together and become a larger wave. Okay? Vice versa. If two waves are perfectly out of phase, like this, and their crests correspond to their troughs, and their troughs correspond to their crests, guess what happens? They totally cancel each other out, and you get deconstructive interference. So it's amazing. You could have you could possibly happen, doesn't happen very often, but it could possibly happen that you have two swells destructively interfering with each other, and it actually creates a calm sea. It could be two huge swells constructively or deconstructively interfering with each other, and it would create a calm sea. Doesn't happen that often, but it could. Now, sometimes, I shouldn't say sometimes, but almost 99% of cases, you get two swells that are out of phase. Okay, they don't constructively. Sometimes they're deconstructively interfering with each other. Sometimes they're deconstructively interfering with each other. And so if you see this, you get a really erratic pattern, right? Sometimes you'll get a huge wave, followed by a little one, followed by another huge one, and then like a flat ocean for a little bit, and then more big waves as the two different out-of-phase wave sets interfere, okay, either constructively or deconstructively. So you can actually see this in this GIF. Now look carefully. This guy's creating two sets of waves. Notice how right there you get deconstructive interference, okay? Look again. See, do you see how right there in those stripes that I drew, there's another one right there, you're getting deconstructive interference. And there's actually a flat sea right there, right? There are no waves. Okay, y'all see that? So anyway, that's deconstructive interference. So it's kind of interesting because this can actually create the phenomenon of rogue waves. If you have two swells that are kind of like mostly deconstructively interfering with each other, but they're a little bit out of phase, it could create a random rogue wave that could be very strong. If you have two strong swells that are mostly deconstructively interfering, you can get this illusion of a flat ocean. But then what can happen is all of a sudden a rogue wave can come up from, so you could be something like this, where they're kind of close to being in phase, but not quite. So they're deconstructively interfering, but then all of a sudden they will start to constructively interfere. Okay, so there's actually a real story about a rogue wave that can cause great catastrophe, right?
Scientists are using the latest technology to hunt for the cause of ship-sinking rogue waves. New research suggests that some of these monsters form in storm systems.
I guarantee you there's such thing, and they're out there, and they want to take your soul.
That's pretty
but
dramatic.
Mysteriously, there are stories of some rogues appearing on clear days. And a recent incident that killed 6 people off the coast of Tofino, Canada, could provide valuable clues. The 65-foot Leviathan II was taking a small group on a whale-watching tour.
It was a gorgeous day out for the end of October. Very similar to a day like today, actually. Beautiful day to be out on the water.
Dwayne Mazaru was on board when the ship got into trouble.
And this is what I remember. The waves kind of seem to come from all different directions out here. Eh?
For the first time, Dwayne is visiting the exact location of the accident.
So the day of the accident, we were on the other side of these rocks here, and watching the sea lions from that side, watching in. We had turned around, and we're coming around that side of the reef there when we slowed down again, and that's when we were struck by a wave coming this way. Just toppled the boat over. Within a split second, I was underwater.
Survivors describe the wave towering over the 16-foot tall boat, a huge wave that came from nowhere.
I was able to swim out from underneath.
So I think you get the idea. But those rogue waves really can be developed, can originate from constructive and deconstructive interference of various swells, wave trains in the ocean. Okay, so what happens when waves reach the shore? So you know that when waves reach the shore, they break, right? They break. What does that mean? Well, as deep water waves start to transition into shallow water waves, they start to slow down. They slow down because when they reach the shore, they get into progressively shallower water. And as you know, a shallow water wave, the speed of the wave totally depends upon the depth of the water. Now, once you get into shallower and shallower and shallower water, it slows down more and more. Again, think of the cars moving along on the freeway. When they're moving fast, they're spaced out. But when they start to slow down, they all crunch up together. Same thing happens with waves. So you can see that the wavelength progressively decreases. It's long out here in the deep water, but it gets smaller and smaller and smaller and smaller as you get closer and closer and closer to shore. The wave slows down. It slows down more and more and more as it gets closer to shore. The wavelength decreases more and more and more as it gets closer to shore. Now remember that a wave, the size of a wave is limited by the size of the wave is limited by the wavelength. So if the wavelength decreases, then the wave can only be 1/7 of the wavelength. So if the wavelength keeps shortening, the height of the wave keeps shortening as well. So it has to start to break, and that means that water starts to tumble down the sides of the wave. Okay, so that's all what I explained here. So as the wave, right, longer wavelengths are moving in the deep water. They're moving faster because their speed is controlled by the wavelength. Deep water waves. When waves approach the shore, they transition from deep water waves into transitional water waves. They start to feel the bottom of the shore. As the waves approach shore, they slow down because speed is controlled by water depth, not by wavelength. That shortens the wavelength, but it does not shorten the period. The wavelength shortens. It makes the wavelength reach the critical 7-to-1 ratio, and the wave becomes unstable. So the wave height to water depth reaches a 3-to-4 ratio. The wave breaks in the surf zone. Okay. And you have what are called breakers, right? So breakers are the surf. That's when the wave is reaching the shore, and it breaks. The wave is breaking down because its wavelength has become so small it can no longer maintain that 1-to-7 ratio. You have different kinds of breakers. Gentle sloping beaches, you get kind of spilling waves where the wave is slowly breaking down. But when it's steeper, you get things like plunging breakers. You don't get things like that so much here in Corpus Christi because usually the continental shelf here in the coastline is pretty shallow, and it's not the steepness of the coastline is pretty shallow. But places like Hawaii, definitely not the case. You get these plunging breakers that are a joy to surfers. So surfers like breakers like this, right? This is what they enjoy. So that's a plunging breaker. Okay. It goes on for 33 minutes. Where are the biggest waves in the world in terms of surf waves? So sometimes you can get 50-foot waves actually hitting the shoreline. That's at Nazaré, Portugal. Okay, so we'll take a look at that. Pretty amazing waves.
Nazaré, Portugal. To spectators and surfers alike, it's becoming famous as the eighth wonder of the world, home to the largest waves on the planet.
This is the final frontier.
Is the 100-footer possible, or is it
Is it a myth? I don't know if it. I think here, if anywhere, it'll be here.
Surfers come to Nazaré with two goals in mind: to ride the biggest wave of their life and to stay alive.
So anyway, it goes on. There's a whole 60 minutes documentary about it. You can watch if you're interested. So
That wave can kill you for sure. So it's the most dangerous wave in the world. And
I don't know. They say it's 100 foot. Maybe it is 100 foot. I thought they were more like 50 feet. But so anyway, Nazaré. What makes it so interesting and so such a fascinating place? Well, it's due to a couple things. It's due to refraction of waves by the Nazaré's submarine canyon, and the canyon almost acts like a lens that focuses the waves on Nazaré Point in Portugal. Okay, so we're going to talk a little bit about refraction. Just like light waves can be bent by a lens, ocean waves can be bent like a lens too and focused on a certain point. So this is happening. We're going to talk about that in just a minute, right? We're almost done here. I know we've been going on a long time, but we're gonna talk about this in just a minute. We're going to talk about how waves can be bent like a lens, okay? So you're going to see that, number one, things are being focused in on Nazaré. But another very important thing is that there's a submarine canyon right off the coast of Nazaré. And what that means is that there's very, very, very deep water very close to the coast, right, in the submarine canyon. So remember, with the deep water, the waves can be bigger, right? Because the deeper the water, the longer the wavelength. The longer the wavelength, the bigger the wave. Okay. This is a little bit of footage from kind of imaging of the Nazaré Canyon, the submarine canyon that's off the coast of Nazaré. That's where you get the largest waves in the world, at the largest surf waves in the world. Okay, so you can see the imaging of the canyon. Okay, like I said, waves can actually be bent and focused like a lens. Okay, now that's called refraction. Whenever a light wave or a sound wave or a ocean wave is bent, we call that refraction. Okay, so refraction means to bend the wave. Now I want you to take a look at this. If you look at this picture, okay, so here comes. It's kind of even hard to tell where the waves are coming from, but you'll notice that here, look at right here. Whoops. Let's put the draw on pen. Look at how the waves, like that's the direction of the waves there, right? And then you can see that it's getting bent. You can see all these different bends. It's pretty interesting, really. If you're looking at the direction that the waves are propagating in. Here, see how it's getting bent around like this, right? So you can see that it's not like the waves are just coming in from one direction. They're getting bent and refocused by the shape of the shoreline. Okay, so why does that happen? All waves, whether they're ocean waves or light waves or sound waves or seismic waves or whatever, bend when they enter a medium that has a different speed. Okay, so you know that waves, ocean waves, cannot propagate through shallow water as fast as they propagate through deep water, right? Imagine this. Imagine you had a marching band of guys all marching, playing their instruments, and they're marching in these rows, okay? And they start to move off of the pavement. They're marching along. They start to move off of the pavement onto the sand. Well, as they move, the people on the sand cannot move as fast. And see how they start to crowd together, more like this? And what happens is the wave bends as it enters the sand. Do you see that? The same thing happens with any kind of wave. Okay? When the wave slows down, it starts to bend. And it doesn't matter if it's a light wave or a sound wave or an ocean wave or anything else. Okay? So the same thing happens with light, right? Light enters a prism, and notice that it gets, instead of going on in this direction, it bends, right? There's a bend in the wave, and then it tries to enter the air again, and it bends again, okay? So even light, when it enters, because light is a wave, as it enters a prism, it bends. Because why? Because it slows down when it enters the glass of a prism, okay? Well, light cannot move as fast in a prism as it can in the air, right? And the same thing happens with waves, right? So you can see the waves coming in like this, but as they reach the coast, they turn, right? You see that? There's a turn. So why is that? It's because you can see that right here, they must have slowed down, right? This is slow, this is fast. So they reach the coastline here, and all of a sudden they slow down, and because they slow down, they bend, just like you see happening right here, okay? So they slow down. The shallow water, it gets shallow, it slows down the wave. Okay, so then there you end up with refraction. Okay, so you all see that, right? So it's going to show you that you're going to see that water will end up getting refracted and bent, and this becomes very important when we start talking about coastlines, which should be in the next few lectures. So anyway, I hope you enjoyed the lecture, and I will talk to you next time. Okay.